We will study in this video the sum constraint. The signature of the sum constraint is the following. You have a sum of variables, x, that you want to sum, and the sum of these variables of x should be equal to the variable y. Let's try to discover a small example, the values that we can remove from the domains if we would apply a domain-consistent filtering algorithm. So, to decide which value should be removed, I propose that we consider each of them and then we see if there is a combination of the other two domains that could sum to 6. So if we take the value 1, for instance, it means that you should be able to sum to 5 with two values from x1 and x2, and that's the case because you can take, for instance, 5 and 0. So 1 is a valid one. What about 3? If you take 3, it means that you need to sum to 3 together with x1 and x2. And clearly that's not possible because with 0, you see that the only one here should be 3, and it's not available. With 2, you should need 1, it's not available. And with 3, you would need a 3 there, and that's not available. So that one should be removed if you apply a domain-consistent filtering for the sum constraint. For the same reasons, the 2 can be removed from that one, the 4 can be removed from that one, and last one is the 6 that could also be removed, because if you take 6, you need to have a 0 with this one, and that's not possible. If you would take 0 there, you see that you have at least a value of 1 there. Therefore, 6 should be removed. But how difficult is it to remove these values? Can we design a filtering algorithm that would be able to remove these values efficiently for the sum constraint? Unfortunately, the answer to that question is no. It's not easy to do. The problem is NP hard, and we can reduce the subset sum to the domain consistent filtering algorithm for the sum constraint. What is the problem of subset sum? So the problem of subset sum is the following. You are given a set of values from S, that's the set of all the values, and you would like to discover a subset of these values that sum exactly to 0. So let's see one example here. So if S is this one, the one that I have highlighted in green, they sum to 0. So you take 9 plus 5, that's 13, minus 13, that's 0. So the answer here is yes, there is a subset sum of 0. But for this set, you can try every possible combinations and you won't be able to find a subset of this value that would sum to 0. This problem is NP hard. Okay, and the answer to that problem is yes, there is some that's a subset of the values that sum to 0, or no, there is not. So it's a yes-no answer. So now that we understand the subset sum, can we answer to the yes-no question of the subset sum using a hypothetical domain-consistent filtering algorithm for the sum constraint? And the answer is yes, there is a reduction. Okay, so we can reduce the subset sum problem to our problem of domain consistency filtering for the sum constraint. And the reduction is the following. That's the starting set of the subset sum. That's all the values that are present in the set at the beginning. And I will encode for each value, I will create a variable xi. For each value ai, I will create a variable xi with the domain, with two values in the domains. It can take the value 0 or the value itself. And for the variable y, so the target of the sum constraint, I will create a domain with 0, okay, because that's the value that I want to reach with my subset sum problem. Then I post my sum constraint between the x variables and y, and I will ask to my domain consistent filtering algorithm to filter all the infeasible values from the domains. There might be two outcomes. The first one is I detect that after the filtering, I see only zeros everywhere in the domains of all the R variables. What it means in that case is that we can answer no to the subset sum because we can say that there is no subset that would sum to 0 in the initial sets of value S. If you can find at least one variable with a domain that is not fixed to 0, then you can answer yes. It means that there is a solution for the subset sum problem, to the initial subset sum problem. That's the reduction. What is the consequence of that? the consequence is that we can reasonably not achieve domain consistency for some constraint with a propagator. That would be too expensive. We do not want to pay an exponential, possibly exponential cost in a filtering algorithm in every node of the search tree. That's really rarely pays off in practice to do that. So instead of looking for a domain consistent filtering algorithm that would be too expensive, we will use a relaxed version of domain consistency, and as you might expect from the first video, that will be bound consistency. And so we will prefer to use a bound consistent filtering for the sum constraint. This will be the topic of the next video.